potentially heated from below to the point that they're uninhabitable. And then it's also, there's some interesting orbital dynamics that can arise in some of these systems. I mentioned that that's my background is orbital dynamics, and so I'm going to show you a fun result towards the end of the lecture about some of the things that planets can do to each other. It's really quite terrifying. You'll see. All right, so let's start off with that first point, that stars dim over time, that they're bright initially. It turns out that a star like TRAPPIST-1 actually takes 1.5 billion years to reach the main sequence. That's where hydrogen burning turns on. What's happening is that the gas from the molecular cloud is slowly condensing and collapsing into what's going to become the star. It's a protostar. But it doesn't get the pressures built up in the centers of their stars very quickly. So you don't start fusing the hydrogen into helium right away. Instead, what's happening is you're seeing basically a glowing ball of gas. And just as it compresses, it heats up, and so you're actually watching just sort of a non-nuclear explosion happening. It's just bright because it's dense and it's got a lot of pressure. So it's slowly contracting, but it drops by a factor of 100 times or so for the case of TRAPPIST-1. But at the same time, the planets are going to form in only like 1 million years. It actually turns out that those planets should form more rapidly than those in our solar system. So the planets form in 1 million years, but the star takes 1 billion years to form. And I think most astronomers or most exoplanet scientists now believe that this dimming early on is the biggest obstacle for planets like those orbiting TRAPPIST-1. And I'm going to show you a movie that sort of highlights this point next. So what you've got here, from left to right, are the 7 planets in the TRAPPIST-1 system. One thing I didn't mention before, but I think you can see it here, is that they all orbit very close to their host star. Right? So the outermost one is at, 0.065 AU or something like that. So we're well inside the orbit of Mercury here, and that's just because the star is so small. Its luminosity is only about 0.01% that of our sun. And so what I've also put on here, with the same colors as my previous video of the habitable zone, is the conservative and habitable zone in its extensions, the orange and the green and the blue. Of course, you don't see them, right? You see black, which means it's not in the habitable zone. The habitable zone is probably about where I am from your perspective right now. The star is so bright that the habitable zone is way beyond these 7 planets that we're so excited to look at with the James Webb Space Telescope. But now, when I start this movie, the star is going to start to evolve, it's going to dim, and the habitable zone is going to come in from the right. So let's get started. There it is, right? Move it in. So it's the 3rd, 4th, and 5th planets in the system that we're most interested in. And you can see it's taking hundreds of millions of years for the habitable zone to arrive to those planets. Now, thankfully, it does move in quickly, and then it kind of slows down, right? It asymptotes to the habitable zone for the main sequence. But you can see it takes quite a while to reach some of those inner planets. And so it can take something like 450 million years to reach TRAPPIST-1d, which is one of the interesting planets that we're interested in. And by the way, the names of those planets go B, C, D, E, F, G, H. You know how astronomers are creative with their names. And so that's what, so if I refer to them, that's what I'm talking about there. But you can see that this evolution is still ongoing even 1 billion years later. So I'm going to just show that to you again, so you can kind of watch your favorite planet and see when it finally reaches the habitable planet reaches it. And so I'll only play this for part of the time here, up to maybe 500 million years. But nonetheless, you get the point, right? These planets roast early on, right? They are more like Venus in their early stages than like Earth. So it's a very different type of environment than our solar system. And this leads to some interesting possibilities. In particular, when a planet is like Venus, if it has water, that water gets into the stratosphere. And of course, as astronomers, you hate water in the stratosphere. But as organisms, you should hate it too, because that means that high energy light, UV, X-ray light, can break apart the water molecule. And so you just get hydrogen and oxygen floating around in the upper reaches of your atmosphere. And it turns out hydrogen is really light and able to escape our planet's gravity very easily. So that means you get hot water up in the atmosphere, it's broken apart, and the hydrogen is gone. Well, without hydrogen, you don't have water. And so we have this new problem that these planets dry out. The hydrogen escapes, and the oxygen, interestingly, remains. And this is a bit of a technical figure here. But what I'm showing you is what we did in this simulation, or many simulations, was we started planets like those around TRAPPIST-1 with 10 times as much water as the Earth has, just as a reference point. And what you're seeing there along the bottom axis is basically position in the habitable zone. Those dashed vertical lines represent that conservative area, that green region of those habitable zones, and then you've got those extensions on either side. And so what you can see from the color bar, let's start on the left, is how much water gets lost. You can see that for smaller stars, lower mass stars, you can lose a lot of water, especially at the very bottom of the main sequence of stars down at 10% the mass of the sun, which is right exactly where TRAPPIST-1 is. And so you can lose a lot of water on these planets because it takes so long for the habitable zone to arrive. Interestingly enough, this is also a great way to build up a ton of oxygen. On the right there is the amount of oxygen that gets freed by this process in bars. A bar is a unit of Earth's atmospheric pressure. So we can build up 5,000 times more massive atmosphere made purely of oxygen via this process. And we only went up to 10 Earth oceans here. Should a planet form with 100 Earth oceans or more, you can build up even more of this. So you can really dump an enormous amount of oxygen into an atmosphere. And this is really important as we start thinking about finding life. It means that we could have taken this observation of TRAPPIST-1, one of those planets, and find water and find oxygen, which sounds great, except none of that was formed by life. And in fact, if you do put hundreds or thousands of bars of oxygen into an atmosphere, it's almost impossible for something like DNA to form. Oxygen is just one of the nastiest elements in the universe. It'll just react with everything, and it'll prevent the formation of things like DNA, proteins, amino acids, things like that. So should we find one of these worlds that has a lot of oxygen in it, that's really bad. That means that there's not going to be life there. At least not life as we know it. We'll see if people come up with experiments that explain how life can form in an environment like that, but this probably is a bad thing should we find water and oxygen. And that's a real revolution in the way we think about finding life in the universe. Many people used to think that we want to just find oxygen. Oxygen by itself means life. And now this is one of several processes that have recently been identified that explain or that suggest that oxygen is not the smoking gun for life that we used to think it was. I'm going to take a drink here. This is probably a good time to ask if anybody's got any questions what I've talked about so far. None, all right. Oh, wait, no, sorry. Over here, yes. I'm right here in front. So the question was, do I think that life on other planets would form the same way it formed on Earth? That's a fantastic question, and it's one I don't know the answer to. What we do, and maybe what's implicit here, and this what I should have said, is that when we look to planets and think about what life we might have on them, we generally tend to think about it as being life like on our own planet. And that's not because we think it's like our life on our planet, it's because we don't know what else to look for. Right? It could be very difficult to really figure out and tease out from that spectrum of that other star, or that other planet, excuse me, that's life when we don't even know what that kind of life is like. So it's something that we're definitely worried about, but it's something that we don't really know the answer to whether or not this is how life usually is, or if it's very different from our own. Another question back there, yeah.
Is the habitable zone only star-driven, or is it reasonable to expect that internal forces in the planet, like the tidal heating, actually generate enough wattage density to create the liquid water necessary?
Yeah, so the question is the star the only driver of the habitable zone, or are there other factors? And what I would say is that the habitable zone, generally scientists, astronomers think of it as being purely that star-driven property. But I love your question because it leads me right to my next slide. And that is that there are lots of other processes that matter, right? And as I said earlier, planets face many perils. And what my research is primarily about is going beyond the habitable zone, going into these other processes that could potentially sterilize a world. And tidal heating was the first one that I worked on. And so this image is one that maybe you've seen. It's a 5-frame movie from the New Horizons mission as it flew on its way to Pluto. A lot of people think New Horizons is a Pluto mission. I think of it as an Io mission because I love tidal heating. And this is a volcano called Tvashtar that was erupting as New Horizons sped by Jupiter getting its gravity assist. On Io, if you didn't know, there are weekly supervolcano eruptions. So about once a week, something like what Yellowstone is going to do to us all one day goes off. And that's basically what you're seeing right there is Tvashtar is basically a supervolcano eruption. There's also some really fascinating phenomena like lava curtains. Anybody know what a lava curtain is? It's really apocalyptic stuff. It's where the crust of Io splits open and lava from below spews kilometers into the atmosphere. So just imagine being on the planet or on this moon and you just have a wall of lava in front of you because the ground is literally split open and it's erupted into the atmosphere. So every now and then planetary scientists observe Io and they see so much energy coming out of Io that the only explanation is that the crust is literally just split open. So it's a pretty amazing place. And the kind of the easiest number to think about in terms of how much energy is being generated in Io is this one, the flux of energy through the surface, 2 watts per square meter. So it's sort of like one light bulb, one of your light bulbs, one of the LED light bulbs on the surface, one per meter. That's about how much energy is being driven by tidal heating on Io. But it's also important to remember that with Io, we're talking about a planet and a moon, whereas what I want to think about is a star and a planet, lots more mass, lots more opportunity for enormous amounts of energy, which speaks to that question before, that yes, you can get a lot of tidal heating on these planets. And the tidal heating is driven by orbital eccentricity, so I'm not going to talk about this too much. But basically, as Io goes around Jupiter, it's on a non-circular orbit, and so the gravitational force that Io feels grows and decreases over time, and that flexes the orbit. You can see people mimicking miming it in front of me. Yeah, it's basically it's like squeezing a tennis ball for 1 billion years, right? You're going to pump energy into that tennis ball, and that's what you're doing to Io. Yes, sir.
Yeah, almost 50 years ago, I worked on Viking, and the instruments were skewed to collect information that was biased towards Earth. And the doctor that I worked with, Dr. Van Soyama, who did the gas exchange experiment. And if you were given the job now designing instruments to look for life on Mars, how much different would it be than what it's been done?
Well, I have to be honest that I don't fully understand all of what was done for the Viking mission. I mean, I've taught it in classes and I know some of the basics of it, but I don't know that I'm not enough of a biologist to really know how I would design an experiment for Mars today. So I don't really have a good answer for you on that question, but I would say more generally,